today I am going to work out the example which I have told in last lecture. In last lecture, as you have seen that a plate girder has to design with a certain for a certain load which has been given and the length of the plate girder is given. So, the example was like this, that a riveted plate girder is simply supported over an effective span of 20 meter. So, span was 20 meter and it carries a UDL of 80 kilonewton per meter exclusive of self weight. So, this is 80 kilonewton per meter which exclude self weight. Design the plate girder completely assuming that it is effectively supported in lateral direction. That means, if let us consider Fy equal to 250. So, sigma Bc will be equal to sigma Bt will be equal to say 0.66 Fy, right. That means, this will become 165. So, these are the things we are assuming. Another thing is, say we are using 20 diameter of rivets, power difference of rivets we are going to use, right. These are the things we are going to use. Now, let us start with step 1, that is computation of shear force and bending moment. Now, as you know, the UDL load is 80 kilonewton per meter and for riveted plate girder we have calculated that self weight is as WL by 300, right. So, approximately self weight will be considered as WL by 300, as we have shown while discussing about the theoretical part in last lecture. There we have shown that W, the self weight of the girder, will become WL by 300, where this capital W is the external load, right. So, W is 80 and L is 20 by 300. So, this is becoming 5.33 kilonewton per meter, right, 5.33 kilonewton per meter. So, total UDL will become the external load plus self weight. So, 80 plus 5.33, that will be becoming 85.33 kilonewton per meter, right. So, total UDL we got. Now, the maximum bending moment we can find out. Maximum bending moment will become WL square by 8. So, W is 85.33 and L is 20. So, by 8. So, this is becoming 4266.66 kilonewton per meter. So, maximum bending moment M max we got now. Okay. These are the data which will be required to find out the suitable section. Next, shear force. Shear force will be WL by 2 at the support. Maximum shear force will become, because for the UDL load we know shear force will develop like this, right. So, WL by 2. So, W is 85.33 into L is 20 by 2. So, this is becoming 853.3 kilonewton. So, in this way shear force and bending moment has been obtained. Next, what we will do? Next, we will go to step 2, where we have to find out the economic depth and wave, means design of wave. So, we will find out now economic depth of wave and accordingly we will design, right. So, economic depth, as we know, will become M by sigma Cb or Bt into Tw, sigma Bc or Bt, right, into Tw. Here sigma Bc or sigma Bt is 165 as it is laterally supported, right. So, if we assume sigma BC value as this, and if we assume some thickness of wave, then I can find out the value of d, right. So, d will become m we got earlier 4266.66 kilonewton meter. So, to make it Newton millimeter, we are multiplying 10 to the power 6 by sigma bt, that is 165 MPa, and width of wave Tw means thickness of wave we are considering as 12 mm, right. Now, 1.1 we have multiplied, as we know, because of riveted connections we are using little higher side to be in shape, right, because net area will be reducing. So, we are going to get d as 1614.7 millimeter, 1614.7 millimeter, right. So, in this way we can find out depth of wave. Now, we got 1614, say let us use say 1700 millimeter, okay. We are using in a higher size, right. Then area of the wave plate will become AW as TW into D, thickness of wave was considered as 12 and depth we are providing 1700 mm. So, this will become 20400 millimeter square. So, area of wave AW is becoming 20400 millimeter square, right. Now, check for shear, we have to check for shear, that is tau V cal is equal to V max by D into TW, right. V max we have already calculated, maximum shear force, that is WL by 2 we have calculated, that is 853.3 into 10 cube Newton, and D into TW is nothing but AW, which is calculated here 20400 millimeter square. So, this is becoming 41.82, and tau V allowable is 100 for FY 250 for this case, right. So, we are seeing that this is less than 100 MPa, so it is okay. So, the depth whatever we have considered, the thickness of the wave whatever we have considered is perfectly okay from shear point of view on the wave. So, in this way the dimension of wave has been decided, right. Dimension of the wave has been decided in this way. Next what we will do? Next we will go for dimension of a flanges, means how to find out the flange width and flange thickness, right. Now, let us design the trial section by flange area method, okay. From flange area method, as we know, the total net flange area will be required A dash FT is equal to say this m by sigma b dash into dE. Here sigma b dash will be nothing but sigma b, that is 165 MPa, and effective depth will become here say 1700 mm, okay. With the trial section we can find out. Now, area of flange will become m by sigma b into d. So, m is 4266.66 into 10 to the power 6 Newton millimeter by 165 MPa sigma bt, and 1700 is the depth. So, after calculating this we are going to get 15,210.9 millimeter square, 15210.9 millimeter square. So, in this way we are going to get the total net flange area flange area we are going to get. So, net area of flange can be find out now, that is AFT by 3, right. So, assuming 20 mm diameter of rivets for connecting flange plates to flange angles and flange angles to wave plate. Now, we are assuming 20 mm diameter of rivets to connect flange plates to flange angles and flange angles to wave plate. That means, if we see, this is the flange and this is the wave. So, when we are going to connect say with channel, say we are going to use 20 mm diameter rivets for connecting flange plates to flange angles, right. So, this is also we are providing 20, this is also we are providing 20 flange angles to wave plate, right. So, all are 20 mm, 20 mm diameter power driven soft rivets let us use, right. So, now let us provide 4 angle section of say 150 by 150 by 10 at 22.8 kg per meter with smaller leg vertical and each having a area of this. In fact, here leg are same. So, there is no scope of making smaller, generally smaller leg we used to keep vertical, right. So, A will become this area of the ISA section, which we will get from SP 6 the structural handbook, that is given 2903 millimeter square, and similarly IXX is given 622.4 into 10 to the 4 millimeter square, and distance of CG from top it is 40.6 millimeter. Now, if we use 2 plates of 400 by 16 mm each having total gross area will become this one 12,800 millimeter square, 2 plates of 400 into 16 mm. So, this will become 2 into 400 into 16, right. Now, for rivet, the computations for gross and net area are shown in the table. The net area has been computed on the assumption that 3 rivets exist at a given section. So, with these assumptions, we will find out gross area and net area, and these are shown here, right. Like say ISA 150 by 150 by 10. Now, gross area of the flange will become this. These values in fact, we are going to get from SP 6. So, 2 into 2903 which will become 5806 millimeter square, and deduction for the rivet hole will become 4 into 21.5 into 10 mm. So, this is becoming 860 millimeter square. So, finally, the net area of the flange we will be getting the gross area minus the hole, that is 4946. So, this is how we can find out net area of the flange. This is in millimeter square. Similarly, for flange plates, 2 number of flange plate of 400 by 16. So, the area will become 2 into 400 into 16 is equal to 12,800. So, area of flange is becoming this, and the deduction for hole will become this one 2 into 21.5 into 16 plus 16, that will become 1736, because 2 plates are given, right. So, 1736, right. So, we can find out the net area as 11424, right, 11424. So, Now, we can find out that area of flange means total area of flange, that will become how much? That will become, if we see that this area plus this area, total will become this, right. So, total area of flange will become like this, and similarly net area, total net area will become this, right. So, in this way we can find out. Now, equivalent wave area will become this, equivalent wave area 1700 into 12 by 6 as per the formula, that will become 3400, right. So, if we go on adding with this again, so AFT will become 22006, 22006, and here the net area will become this 18920, right. So, in this way we can find out. Next, so thus total net flange area AFT is becoming 18920 millimeter square as against the required area of this millimeter square, right. Now, we will find out IXX. IXX will become what? 1 by 12 BD cube, B is this because of this wave, 1 by 12 BW into DW cube, I can say, where DW is 1700 and BW is 10. So, this plus this is because of angle, 4 angles are there. So, 4 angles, its own moment of inertia is 622.4 into 10 to the 4 plus AR square, right. Area of angle section is given and the distance is can be find out. So, from that the moment of inertia due to the additional I section, angle section has been found, plus 2 into 400 into 32 into 815 into 815 plus 60, this is due to additional plate, 2 additional plate of 400 width and 32 thickness, 16 into 16 thickness, 16 by 16 means 16 1, another is 16. So, and the distance will be 815 plus 16, right. So, finally, if we calculate this value, we will be getting this value, that is 3174,036.1 into 10 to the power 4 millimeter to the power 4. So, in this way we can find out IXX value. Now, what we will do? We will check for bending stress, So, bending stress, what will be? Sigma BC calculated or sigma BT calculated, where maximum is, and in this case both will be same, right. So, this will become m by I into y. So, m was calculated as this 4266.66 into 10 to the 6. Earlier, if you see, this was calculated, and I was calculated 3174,036.1 into 10 to the 4, and y max is 882. Y max is 882. So, the values are coming 118.56, which is less than the value 0.66 Fy, that is 165 MPa. So, from bending stress point of view, this is okay. So, the flange whatever we have chosen for the girder is quite okay, because it is below the permissible limit. The developed stress in compression or in tension due to bending is under permissible limit, that is less than 165 Newton per millimeter square. So, in this way we can check it. Next what we will do? Next we will go for curtailment of flange plates. As we know, because of UDL load, the moment will develop like this. So, we do not need to provide the bigger section throughout its span, because maximum moment is here. So, we can provide larger section in this central near the center and smaller section near the support, because near support moment is going to be less and at support it will be 0. So, in to take the advantage of this moment, means advantage of the type of nature of the developed moment, we can curtail the plates at a certain distance, right. So, that we can do. Now, as we know, the maximum bending moment is 4266.66 kilonewton meter, right. So, moment of resistance has to meet similarly 4266.66 kilonewton meter, right. Now, let us theoretically find out the length of cut-off plate, and let us consider that is say 2x1. So, then x1 we can find out if we introduce 2 plate, then x1 we can find out in this way, that is half into L into A1 by AFN to the power half. So, if we put the value, L is 20 meter span and A1 is 5712, which we have calculated, and AFN also has been calculated, that is 18920, and if we make square root of this, then finally we will get x1 as 5.49 meter, right. The plates to be extended beyond their theoretical cutoff points. Remember, now plates to be extended beyond their theoretical cutoff points, the value of bending moments at the theoretical cutoff points are found as follows. Value of bending moment we can find out from here, right. As you know, equation of parabolic bending moment diagram can be given here, y is equal to 4a by L square into x into L minus x. Now, distances of to section for theoretical cutoff x can be found, that is L by 2, this is 10 minus 5.49, that will be 4.51, and L is given this and area A is given this. So, using this value we can find out, that is 4 into 4266.66 into 4.51 into 15.49 by 400, that will be this much 2980.68. So, bending stress in compression in the topmost cover plate can be find out and can be checked. Now, the gross moment of inertia of section cutoff the topmost plate M1 will become this one, right, and the distance up to the center of the topmost cover plate Y1 will become this 850 plus 16, this is because dW by 2, that is 1700 by 2, 850 plus 16 plus 16 by 2. So, this is 874. So, now we can find out the sigma BC calculated. Sigma BC calculated will be how much? That is M1, that is 2980.68 into 10 to the 6 into Y1 by I, right, M1 by I into Y1. So, 2980.68 into 10 to the 6 into 874 by 31740.361 into 10 to the 4. So, if we calculate, we will get the value 82.07 Newton per millimeter square, right. So, in this way you can find out the sigma BC cal, and which is less than the allowable permissible stress, that is 0.66 Fy, that is 165 MPa, 165 MPa. So, this is quite okay, right. Similarly, sigma BT cal can be find out, right. So, sigma BT cal when we are going to find out, we can find out with the same linearly interpolating, we can find out, right. This was sigma BC cal. So, little more will be the sigma BT cal, that is 95.456. So, this is also okay. Now, we will find out the tensile force in cover plate. Tensile force in cover plate will become how much? The stress is 95.456. So, this into area, right, by 1000 if we make, it will become kilonewton, that F is becoming 545.21 kilonewton. So, in this way we can find out the tensile force in cover plate as 545.21 kilonewton, right. Now, the rivet value. So, if we use 20 mm diameter power driven rivet, power driven soft rivet, the strength of rivet value in single shear can be find out, that will be pi by 4 into d square into tau Vf into pi by 4 into d square for single shear. So, pi by 4 into d square, that will be 21.5 square into tau Vf is 100, and to make it in kilonewton we are dividing 1000. So, we are getting 36.3 kilonewton, right. So, rivet value we are going to get due to shear, and due to bearing the rivet value will become sigma Pf into d into T. Sigma Pf value is 300 MPa and diameter is 21.5 and thickness is 16, right. And if we divide by 1000 to make it kilonewton, then finally the value will become 103.3 kilonewton. So, strength of rivet in single shear is becoming 36.3 and strength of rivet in bearing is coming 103.3. Therefore, the rivet value R can be taken as 36.3 kilonewton. So, in this way we can find out the rivet value of that with 20 mm diameter of power driven soft rivet. So, the moment we get rivet value, we can find out the number of rivets at the section. So, what will be the number of rivets at the section? That will become the force whatever we got here, right, the shear force 545.21 kilonewton, tensile force at the cover we found, that by rivet value means F by R. Say from this we are going to get 15.2, right. So, we are going to get 15.2 and say let us use little high, say 20 or 60, means 16 is minimum required, right. Now, providing say 20 number of 25 PDS power driven soft rivet. So, these rivets are provided in 2 rows in the extended portion of the plate beyond the theoretical sections with 1.5 times diameter of rivets as edge distance and 3 times diameter as pitch distance, right. So, what we are doing, that we are assuming that 3 times diameter as pitch distance and 1.5 times diameters of rivet as edge distance. So, edge distance will become at least 1.5 into 20, that means 30, and pitch will become 3 into 20, that is 60, right. Now, actual length of cutlement of topmost cover plate will become this 2 into 5.49, that is the length whatever we have calculated, plus 3 into 21.5 into 10 by 1000 for making it meter. So, we are going to get 12.27, right, 12.27 meter. So, now in next step, so curtailment is over, next step is the connection design. We will go to design the connections, right. So, step 5 will be design of connections. Now, for that we need to know the distance of the CG of the compression flange from the top. So, distance of CG the compression flange from the top. Now, if we see, this is the plate girder. Okay. So, what will be the distance of the CG of the compression flange from the top? That will become how much? As you know, 400 is the width we have provided, 400 into 32 into 16 plus 2 into 2903 into 32 plus 40.6 by the area, that is 400 into 32 plus 2 into 2903, which is becoming 33.66 mm. So, DE will become 764, that is total, minus 2 into 13.66, because CG distance, this is 33.66. So, DE will become this one, the distance between CG of the flanges, DE. So, that is 1764 minus 2 into 33.66, that will become 1696.68 millimeter. So, this is how we can calculate the value of DE. Next, connections of flange angles to wave in compression flange. We will find out the connections of flange angles to wave in compression flange. Now, load on compression flange per millimeter length can be find out, per meter length can be find out as 80 kilonewton per meter. Now, if we use 20 mm diameter of power driven shop rivet, then strength of rivet in double shear will become this, 2 into pi by 4 into d square into tau wave. Why double shear? Because if we see, so suppose this is the wave and this is the flange of the plate girder, so top flange, right. Now, we are going to use some angle here, we are going to use some angle here, right, similar to in the bottom also. Now, when we are connecting this flange with the angle, it is in single shear, this is in single shear, right. So, accordingly we have find out the rivet value. Now, when we are going to connect this, we will see this is in double shear, right. Therefore, we need to find out the strength of rivet in double shear, this is in double shear, right. So, strength of rivet in double shear will become, what will happen, 2 into pi by 4 into d square into tau v f, right. So, 2 into pi by 4 into d square, d means 20 mm diameter we have taken. So, gross diameter will become 21.5 into 100, that is tau v f, by 1000 to make it kilonewton. So, the strength of rivet in double shear is becoming 72.61 kilonewton, and strength of rivet in bearing, will be what, that is sigma p f into d into t. Now, d value is 21.5, t is thickness of the web, right, that is given 12 mm, right, into sigma Pf. By 1000 we are making to make it kilonewton. So, this is becoming 77.4 kilonewton. So, in this way strength of rivet in bearing also we are going to get as this. Now, the rivet value can be find out from these two, that is the lesser value of these two. So, rivet value will become here R is equal to 72.61 kilonewton. So, in this way we can find out, right. Next what we will do? Next we will find out pitch. So, rivet value as we have got 72.61 kilonewton, we can find out the pitch. Pitch can be find out from this formula which was derived earlier. In fact, this I have not derived in my lecture, which can be found from any standard book, right, that how to find out pitch, right. That will be this one, R by V by dE into AF by AF plus 1 by 6 AW whole square plus W square, right. This is basically horizontal force, say H, and this is say HR, sorry RH, right. Because of shear, R means shear force will come in horizontally, which I am giving per unit length as RH, and because of vertical load, say W is coming per unit load length, per unit length W, and this is RH, right. So, the resultant will become this plus this, where RH is becoming V by dE into AF by AF plus 1 by 6 AW, and that we are finding out from the expression what has been done from derivation, right. So, P we can find out from this value, that is R is 72.61 kilonewton rivet value. So, if we make in Newton, this will become 72610 Newton by this is V. V we have calculated as 853.3 kilonewton. So, for Newton we are making 853.3 into 10 cube Newton, right. V by dE, dE also we have found, dE is what, that the distance between CG of flanges, CG of top flange to CG of bottom flange, CG of compression flange to CG of tensile flange, dE, that is calculated as 1696.68. Then 5860 into this 5860 plus 12800, that is AF, total area, right. Area will become the plate area and the flange area, basically total flange area, whatever flanges are there, 5806 plus 12800, right, AF by AF plus 1 by 6 AW. If we put, and W is 80. So, if we put all this, we will get the value as 167.8 millimeter, right. So, pitch we are going to get as 167.8 millimeter, right. Now, we will go for connections. Now, connections of flange angles to flange plates in compression flange. Let us see how to connect flange angles to flange plates in compression flange. So, in this case also let us use 20 mm diameter of power driven rivets. So, strength of rivet in single shear will become pi by 4 into d square into tau Vf into pi by 4 into d square, because this will be in single shear, right, and 1000 has been divided because to make it kilonewton. So, in this way we can find out the strength of rivet in single shear as 36.3 kilonewton, and similarly strength of rivet in bearing will be sigma Pf into d into T. So, d is 21.5 and this is 10 mm thickness of the angle, and sigma Pf is this by 1000 for making kilonewton. So, 64.5 kilonewton. Let me make clear this. If this is the wave, say this is the angle. Now, this angle is 150 by 150 by 10, right. Now, when we are going to find out the strength of rivet in bearing, we will see we are taking 10 mm, because the thickness of the angle is less than the thickness of the flange. That is why the lesser value has been taken, that is why the value 10 has been taken, and as we are using rivet diameter as 20, so 21.5 as a gross diameter has been taken, and as usual the sigma Pf value, permissible stress in bearing, has been taken 300 in this case. So, in this way we are going to get the strength of rivet in bearing as 64.5 kilonewton, right. So, we can find out the rivet value finally as 36.3 kilonewton. Now, we can find out the pitch between the flange and the angle in compression flange, right. So, pitch will become R into dE by V into AF1 plus AW by 6 by A1 plus A2 up to AN. In fact, this expression you will get in any standard book. This has not been derived because of shortage of time, right. But here I am, in fact, this pitch has been derived for the weld connection. In case of weld connection I have tried to show, and as in weld connection I have shown, I have not shown in rivet connection. That is why when I am taking the example, I am taking example for rivet connection, so that you can have some idea, right. So, pitch we are going to find. So, if we put the values, say R means rivet value, that is 36.6 by V we know the shear force, which has been calculated as 853.3 kilonewton. So, to make it Newton, 1000 I am going to multiply, right, and dE is 1696.68, which has been calculated, right, and the area of this total AF1 plus AW by 6 is becoming 22006. AF1 plus AW by 6 is becoming 22006, and the area of flanges are, means area of plates for flange is 12800, right. So, in this way I can find out the pitch, which is becoming 124.08 mm, and if rivets are used in 2 rows, then pitch will be 2 into 248, means 2 into P, that will become 248 millimeter, right. Rivets, let us assume that rivets are used in 2 rows. So, in this way you can find out the pitch as 248 millimeter, right. Next, what we will do? Next, connections of flange angles to wave in tension flange. Connections of flange angles to wave in tension flange means this one. Tension, we are assuming that this is this is the flange, this is happening at bottom, right. Connections of flange angles to wave in tension, right. That means this one, here tension is going to develop. So, from earlier steps we have seen the Rivet value will become finally 72.61, because we have to check Rivet due to double shear, here double shear will happen, and Rivet value due to bearing. So, from these two conditions we will find out the least one as 72.61 Rivet due to double shear, right. And tension flange is unloaded flange. So, W can be made 0. So, P can be found simply from here, right. As in tension flange there is no load, only in compression flange load is there. So, at the top load is there. So, W means plus W, that will be not there. So, only the RH will be there, that value, forces in horizontal direction. So, if we put the values, the P will become R by V by d E into A dash F by A dash F plus 1 by 8 A W. Now, putting those value, R as 72.61 means 72610 Newton by 853.3 into 10 cube, that is V, the shear force, and D is effective depth, that is 1696.68 millimeter, and then A dash F is 16370, this is A dash F, and A dash F plus 1 by 8 A W is this one, as we have calculated earlier, 18920. So, now putting all this value, the P will get 166.86, that means 167, which we are going to get as 167, right. So, maybe we can use say 160 or 165, right. So, in this way connections of flange angles to wave in tension flange can be made. Now, we will go for connection of flange plates to flange angles in tension flange. So, this is, so 4 cases are happening. If we see 4 type of connections are happening, and we have to find out the number of rivets or the pitch distance properly, right. So, in this way it was. Now, what will be the pitch distance here, what will be the pitch distance here, what will be the pitch distance here. So, in compression and again in tension, this is one, this is another one, this is connection of flange plates to flange angles in tension plate, right. This is case D, this is case C, this is case, this is case A, this is case B, right. So, 4 cases are happening, right. So, here rivet value we will get 36.3 kilonewton, as earlier we have done in case of compression flange. In case of compression flange already we have calculated the rivet value. So, we can find out the pitch. Pitch will become R d E by V into A F dash plus 1 by 8 A W by A dash P, right. Now, if we put those value, R is 36.3 kilonewton, right. So, that has to make Newton actually, right, and V is this one 853.3 kilonewton. So, this also we are making in Newton. Then D is given 1696.68, D is this is 1696.68 millimeter. So, D we got, then AF dash plus 1/8 AW, that is given the value as 18920, and A dash P is calculated earlier, that is 11420. So, we are going to get as 119.5 millimeter, 119.5 millimeter. So, if we use 2 rows for the rivets, then the spacing will become, pitch distance will become 239, right. So, in this way we can find out the spacing. Next, we will go for design of stiffener. This is the last step. So, as you know, UDL load we have already including self weight, that is 85.33 kilonewton per meter. Then total load will become this, and support reaction as we have calculated earlier. So, sigma p will become 0.75 into Fy, that is this. So, bearing area can be found from this equation, that is 853.3 into 1000 by 187.5, because this is the sigma p, right. So, from this bearing area we can find out, that is 4550.93 millimeter square, and if we consider radius at root R1 for flange angle will be then 12 mm, then select a 4 ISA of 110 by 110 by 12. Then bearing area has to provide like this, 4 into 110 minus 12 into 12, that is bearing area will be 4704 millimeter square. Now, we have to check for load. So, actual length we have 1700 minus 2 into 10, so 1680 millimeter, and effective length of columns will become 0.7 into 1680, that will be 1176 millimeter. So, cross sectional area will become 4 into 2502 plus 2 into 20 into 12 into 12. So, this is becoming 15768 millimeter square, and the moment of inertia of the section about the center line of wave can be find out from this equation, that is 4 into 279.6 into 10 to the 4 plus 4 into 25.02 into 3.16 plus 1 plus 0.6 whole square into 10 to the 4 plus 1 by 12 b d cube, that is 2 into 20 into 12 into d cube, 12 cube. So, I we are going to get as 3392.08 into 10 to the 4 millimeter to the 4, right. So, then what we will do? Now, we will find out the radius of gyration of column section about the center line. So, radius will be I by A, square root of I by A. So, I was found 3392.08 into 10 to the 4, and A is 15768. So, R will become 46.38 millimeter, and the slenderness ratio of column section will become L by R equal to 1176 by 46.38, that will become 25.35, right. So, from IS 800 1984, allowable stress in axial compression for the steel having yield stress of 250, sigma AC can be found out this. So, from table of IS 800 1984 we can find out the permissible compressive stress as sigma AC as 146.395 Newton per millimeter square for L by R ratio as this, and for Fy 250. So, load bearing capacity of stiffener can be find out from this formula, that is 146.395 whatever given here, right. Then this is the sigma AC into area. So, this value load bearing capacity is becoming 2308, which is greater than 1706.6 kN. So, it is okay, that means the design of bearing stiffener is quite okay. Now, connection of bearing stiffener to wave plate by using 20 mm diameter power rivets, we can find out the strength of rivet in double shear as this. Earlier also we have got. So, I am quickly trying to finish, right. Earlier for double shear we know the rivet value is 72.61, right. So, the strength of the, again similarly in bearing it is 77.4, that also we have calculated. So, rivet value is becoming 72.61, right. So, therefore, rivet value is 72.61. So, number of rivets we can find out, load by rivet value, that is 11.75. So, let us provide 16 rivets in 2 rows. Okay. So, some rivet we are going to find out, means say generally we used to provide little higher side, right. So, whatever we are getting in summary, if we see that we are going to get this, right. 2 plates we have provided. I am not showing here cutlement, just section at the mid where I am trying to show. So, these are the details, right. Now, this I section is ISA 150 by 150 by 10, right, and this width of the flange is 400 and this is 16 mm, 2 plates we are providing, right, and this distance is becoming 1615 or 1700 we have considered, right. It was coming 1615 and we have considered 1700, right, and cutlements at 12.27 meter we have done, and number of rivet where we have provided 16, little higher side we have provided, right. And what else we have done, that pitch in compression flange, that is flange angles to wave, we got 167 millimeter. Similarly, flange angles to flange plate, we got 248 millimeter, right. And similarly, pitch in tension flange, how do you get flange angles to wave, that we are getting 166, and flange angles to flange plate we are getting 239. So, these are the data we got after designing, right. So, in summary, if we see the design details, this is like this. So, with this I like to conclude today's lecture. Thank you very much for your patience to listen this lecture. Thank you.